Lesson 13.3, Task 1. Investigate geometric sequences. A geometric sequence is a sequence in which the ratio of the successive terms is constant. The constant ratio r is called the common ratio, where r is not equal to 0 and r is not equal to 1. You can write a rule for a geometric sequence using function notation. A of n equals a of 1 times r raised to the n minus 1 power, where a of 1 is the first term and r is the common ratio. In subscript notation, the general rule is a sub n equals a sub 1 times r raised to the n minus 1. So you have two formulas. Here's function notation and here's subscript notation. They both are the same formula, just different notation. So you would get the same answer no matter which formula you use. All right. Waclaw Sierpinski designed the triangle fractal shown below. Sierpinski began with a solid triangle. In each subsequent stage, he divided each solid triangle into 4 congruent triangles by connecting the midpoints of the sides and then removing the center triangle formed. All right, so if you take this side and find the midpoint, and then you take this side and find the midpoint, and you take this side and find the midpoint, that's how he drew his next triangle. And he did that by finding the midpoints of each one, and he continued that pattern. All right, so it says the table shows the number of solid triangles and the number of removed triangles for each stage n, where the larger removed triangles at each stage beginning with n equals 3 are counted as being composed of the smallest removed triangles at that stage. All right, so what that means is like, okay, so if I have a small triangle, the small triangles are the ones that we're counting here in stage 3. So if I take this white triangle and I can put it here, there's going to be 1, 2, 3, 4 of the small triangles in this larger triangle here. So the removed triangles would be 1, 2, 3, 4, 5, 6, 7. So when you look at the table, you can see stage 3, the number of solid triangles would be 9. So if you count the solid triangles, it would be 1, 2, 3, 4, 5, 6, 7, 8, 9. That's your solid triangles. And then the number of removed triangles as 7. So if you do 7, you're going to see 1, 2, 3, 4, 5, 6, 7. Again, there's 4 of the small triangles inside that larger white triangle there. All right, so that's how they get the 7 here. All right, for each stage, the fraction of the area that is shaded is the number of solid triangles divided by the number of triangles of that size. All right, so the number of triangles of that size, so you got the number of solid and the number of removed triangles. So together, 9 and 7 equal 16, 3 and 1 equal 4, 1 and 0 equal 1. So this is the total number of triangles of that size. All right, so the fraction describing the shaded area of the triangle in stage 1 is solid over total. So 1 over 1 equals 1. What fraction of the triangle is in stage 2? So if we look at solid over total, that's 1 over 1. In stage 2, it's going to be 3 over 4. So 3/4 would be stage 2. All right, notice that the large removed triangle in the third stage can be viewed as being formed by 4 of the smaller removed triangles, okay? We talked about that already. What fraction of the triangle in stage 3 is shaded? So if you look at stage 3, it's going to be 9 over 16. And if you think about 3/4 times 3/4, 3/4 times 3/4 is 9 over 16. So that means our common ratio is going to be 3/4. So it says, what is the common ratio of the terms that describe the shaded area at each stage? All right, the sequence that models the area of the shaded region as a fraction of the total area at stage n is a of n equals 3/4, that's your common ratio, raised to the n minus 1 power. Or a sub n equals 3/4 raised to the n minus 1 power when written in subscript notation. So again, these are two different notations, but you're going to get the same answer. All right, the first 10 terms of the sequence a of n are shown on the graph. All right, so you know the first one was 1, 1. That came from the table. And the second one, if you look at stage 2, it was 3/4. So 3/4 is going to be 0.75, which is going to be right in between 0.7 and 0.8. And then you can see what they did for each one of those is just graph that next point by taking 3 and multiplying it by 3/4 and on down to the 10th term. All right, it says if you continue the graph of a of n, how would you describe its n behavior? All right, so you can see this curve. So it's curving down and it's getting closer to 0. So it's going to probably approach 0 and kind of flatten out there. So it's not increasing, it's getting closer to 0. What type of function has a graph whose shape is similar to the graph of a geometric sequence? So we know linear is a straight line. We know quadratic is a U-shaped graph called a parabola, and exponential is either exponential growth or decay. And if we look at this graph, we can tell that this is exponential decay, and that should make sense because 3/4 is between 0 and 1, and so that represents exponential decay. All right, that's all for task 1. If you have any questions, let me know. Lesson 13.3, task 2. Determine a term in a geometric sequence. Recall that there are two parts when writing a general rule for a geometric sequence. You need to know the first term of the sequence and the common ratio. You can use the general rule for a geometric sequence to determine any nth term. All right, consider the geometric sequence 6, -18, 54, -162, 486, ... To write a rule for this sequence, you need to know the first term and the common ratio. By looking at the sequence of numbers, you can identify the first term as 6. So the first term literally is just the first term in your sequence. All right, the common ratio comes by taking the second number and dividing it by the first, or taking the third number and dividing by the second. So -18 divided by 6 would be -3. 54 divided by -18 is -3, and so on. So our first term is 6, and our common ratio we can conclude is -3. All right, so it says, what do you notice about the signs of the terms of the sequence? All right, so the signs are positive, negative, positive, negative, positive. What does this suggest about the common ratio? The signs of the terms alternate, so the ratio of consecutive terms is negative. And I already looked at that and said -18 divided by 6 is -3. So -3 would be your common ratio. So the common ratio of the sequence is -3. All right. Will the 12th term of the sequence be positive or negative? Explain. All right, so the first term is positive, then negative, positive, negative, and so on. So this is an odd number. This is an even, odd, even, odd, even. So you can see that the odd numbers are positive and the even numbers here are negative. And that pattern will continue as they alternate back and forth. So because 12 is an even number, it will be negative. And the given sequence of numbers shows that the terms having even portions are negative values, so the 12th term will also be negative. And again, when we talk about the even terms, that means just the second, the fourth, the sixth, and so on. Those numbers are negative, so you can assume the 12th term will also be negative. All right, so it says now use the general rule for the geometric sequence a of n equals a of 1 times r raised to the n minus 1 power, where the first term is a of 1 and the common ratio is r, to write the rule for the sequence. The rule in function notation is a of n equals 6, that's our first term, times negative 3, which is our r, our common ratio, raised to the n minus 1. In subscript notation, it's a sub n equals 6 times negative 3 raised to the n minus 1. If you want to determine the 12th term, all you have to do is substitute 12n for n. Okay, so 12 minus 1 would be 11. You would do negative 3 raised to the 11th power times 6. Remember, you always do order of operations, and you can determine that your 12th term would be negative 1,062,882. All right, that's all for task 2. If you have any questions, let me know.